Okay, number 11. In the design process for a child restraint chair, an engineer considers the following set of conditions. A 12-kilogram child is riding in the chair, which is securely fastened to the seat of an automobile. Assume the automobile is involved in a head-on collision with another vehicle. The initial speed, VI initial, of the car is 45 kilometers per hour. The speed, that's pretty fast, I guess. No, it's not. How fast is that? We'll check it in a second here. The speed of the automobile is reduced to 0 during the collision in a time of 0.2 seconds. And assume a constant car deceleration during the collision. So we've got a couple tasks here. First is, we want to estimate what's the net horizontal force F that the straps of the restraint chair must exert on the child in order to keep her fixed to the chair. We're going to do that by treating the child as a particle, and we need to, the second part of this challenge is we've got to state any additional assumptions that we made during our analysis. I'm going to go through the analysis first and then help you pick out where we made the assumptions, because we do that all the time. So we've got a car here. That's obviously what a car looks like. It's traveling at 45 kilometers per hour, which Siri says is 27.96 miles per hour. So pretty safe traveling speed, actually. It's coming to a stop as it has this collision here with some other car, object. Oh, it said a head-on collision, right? So we have our big right here, which what that allows us to know is that our final velocity is going to be 0 meters per second, and the time it took for this velocity to change was 0.2 seconds during that time. So what I want to do first, if I'm going to find what the net force is, I'm going to need to know what is the acceleration of the vehicle during that time, because the child is also traveling 45 kilometers per hour and hopefully safely being brought to a stop by those restraint belts on the seat in the same amount of time. So we have the child's mass of 12 kilograms experiencing the same acceleration that the car is during the collision. So to figure out that acceleration, we also are going to need to know what's that velocity in meters per second, because that's how we're going to be able to relate that all to newtons. So we'll do our quick dimensional analysis here to think about what we've got. 1 kilometer, blah, blah, blah. When I plug that in my calculator, I get 12.5 meters per second is our initial velocity. So now I want to solve for what is my acceleration there. Acceleration is equal to a change in velocity divided by time. You'll notice I'm not using anything more sophisticated because I don't need to. Change in velocity means final velocity minus initial velocity divided by our time interval. So we've got 0 meters per second minus 12.5 meters per second. All that is divided by our time interval of 0.2 seconds. Even though that's such a tiny fraction of time, this is actually considered a pretty safe time interval in the event of a collision. So we get over here that we have an acceleration when I plug that in my calculator. I get negative 62.5 meters per second squared. And apparently I'm going to bump with my pinky and leave a bunch of weird orange marks all over the page. So you can ask yourself, does that make sense? It's a pretty big number, but we're also stopping in a pretty small amount of time, like I said. It's a negative number. Does that make sense? Well, sure, if we defined our velocity as being in the positive direction, then any change in that velocity that's decreasing it must be negative because it's in the opposite direction. So now we can figure out, let's think about what's the free body diagram of the child look like. Well, there's a 12 kilogram mass, a particle, just like the problem told us to treat her, sitting right here. And then what forces are acting on the child? Well, we've got the force that's from her seatbelt that's acting against her body as she is moving forward. Something is counteracting that motion to bring her to a stop. And then we're neglecting to consider the force of gravity acting on her and the normal force right there. So, are there any other forces that we should consider? And this is where some of our assumptions might come in that are important to note. We always make assumptions when solving problems. Think about how many times we've done problems where it says neglect air resistance, or I told you to always ignore air resistance. Come to think of it, isn't that true here? We're imagining there's no air resistance. So there's no other force due to air acting on this child that we're considering. If we look at our free body diagram down there in the corner, we're not including the friction with the seat. So we're really treating her as a free body, a free object. So we're also assuming that those belts aren't going to stretch at all. That there is really just some fixed force. Remember, it could be a Jedi for all that I care that is making her come to a stop. We're assuming that the seat is fully horizontal, that there is no angle that we're considering involved, or that we're considering that might change what direction those forces are really acting, so that there is, in fact, some importance due to those other forces that we are neglecting to include. So those are just some of the assumptions that we're making. So now when I come back down here, if I think about, if it's a horizontal seat where there's no friction and there's no elasticity, then these two forces cancel out, the normal force and the force due to gravity. We don't need to include those. We really have only one force. Our net force in this case that's acting on the child is the force of those safety belts that are holding her in her seat. So they're going to be equal to her mass times her acceleration, which is going to be 12 kilograms times the acceleration we found above, negative 62.5 meters per second squared. When I plug in my calculator, I get 750 newtons is the force that's acting on her. Now, there are more assumptions that you could consider in your design up here. You could think about, well, we're treating the child like a particle, and not like a system of many parts where there's arms and legs and heads that all move independently. We're treating the belt as a single source of force. So those are all things that you could add. There's many, many different ways you could look at and list your assumptions. The ones I've given here are some of the basic ones.